All right. Good morning, everyone. Okay, you have 30 seconds to wrap. Okay. If you have a conversation, so have a good, nice day, sunny outside, Friday, over the conference. And next week you have the study break starting from Wednesday, also good. Can I please catch up with commentary? Or maybe catch up with the sleep. Let's continue our discussion, which got interesting last day when we found that this matrix, which we call it modal matrix, right? The modal matrix magically change our mass and our stiffness matrix to a diagonal matrices. And why it was good? Because we managed to turn a coupled system, n-degree freedom coupled system to many one-degree freedom system, which we know how to solve them, right? Now we're going to add another component to our system, which is damping. All right. So let's see how it will turn out for damping. So I have this system, as you can see, two mass, stiffness, and two different dampers. First step, I need to derive the equations of motion. So we will do that by starting the free body diagrams that we know how to do. So free body diagram for this one and free body diagram for the other one. I have two springs. I have the springs and damping over there, which simply this one will be Kx1, and for dampings C1 x dot 1. One way to check always K and C, the forces are the same direction when you draw the free body diagram, except for dampings, it is velocity. So getting to the one in the middle, we assume that x2 is bigger than x1, right? That's an assumption. You can go with the opposite. That's correct. This is just for the sake of drawing the free body diagrams in the correct directions. So if x2 is bigger than x1, it means the spring is going to have a tension load, and the value will be K x2 minus x1, because we already agreed that x2 is bigger than x1. So I included the sign there. And the damping will be the same, C2 x dot 2 minus x dot 1. So if I have the forces for one side, I know the reaction will be for the other one, the same, the opposite direction. And these guys over there, we know they're going to be under compression because of the direction of x2. So I have Kx2 and here C1 x dot 1. So that's the free body diagram, the very first step, and you should be comfortable drawing the free body diagrams. So then our friends, the Newton law, sum of the force, MA. For x1 and x2, we know how to write them. We will do, and then we put everything in a matrix format. Gives us 0, M, x double dot 1, x double dot 2. And here I have C1, C2, minus C2, minus C2, C1 plus C2, x dot 1, x dot 2. I skipped the math and writing the equation, and I just get to the last part, which is the matrix format. So over here, I'm going to have 2k minus k, and this guy will be 2k. x1, x2 equal to 0. There is no force, unlike the previous example, but there is no problem if there are external forces. Because in previous example, we had external forces. All right, so this is my equation of motions in matrix format. Again, as you saw, I skipped all the calculations and jumped to the idea that we know how these matrices should look like, right? We can do a quick check to make sure our calculation is correct. But in exam, I want you to drive the equations, right? Write all the equations rather than me skipping it and writing the last one. Let's quickly check the equations together. The mass matrix is diagonal because if you remove the springs and dampings, these two systems are independent, all right? I gave you another example, I guess 2 lectures ago. Let's say if you have a cart and on top of that, there is a disk. So this guy is going to rotate with theta and this one is going to move with x. If you remove the spring, theta and x, they are connected, right? So it means your equation later when you write them, you're not going to end up with 0 on off diagonal. So a quick check always, remove the spring, remove the dampings, and move one of them. See if moving one of them result in moving the other one. In the example that we have, it's not. So we expect our mass matrix to be diagonal, or they should be decoupled, as we said before. But we don't need to do that check. If we just write the equations correctly, the free body diagram is correct, then we should get that one. Let's check a stiffness. We know how stiffness should be. First of all, on diagonal, the sum of a stiffness going to each variable. For x1, I have k and k. These two are parallel, right? Because if I move mass, they are going to move the same amount. So I just add them 2k, but again, they don't have to be parallel. It is just a rule. Yes.
The matrix would be non-zero on the
yes.
Yeah. With the spring or without?
Without the spring. Yes. The mass, their acceleration are connected. Yeah. We have example, I guess, 24, that this is something that the masses are connected. Yeah, that's correct. So the stiffness, the diagonal is the sum of the stiffness, and off diagonal with negative sign is the stiffness between these two variables, as you can see, minus k. So good news, the damping matrix follows the same rule as a stiffness. So I'm going to write it down here for you. The damping matrix follows the same rule as stiffness matrix. So look at the diagonal. The diagonal is sum of the damping connected to each variable, and off diagonal, the one that connect these two, which there is one and they are non-zero. If you had no C2 here, right? If you had no C2 there, there was no connection by damping between these two, and your damping matrix would be diagonal as well. But this case, it's not. Right? So that's the various steps that we drive the equation of motion, and we put them in matrix format. Our next step, like I'm repeating the same things that we had before. So let's call this one step 1, free body diagrams, and step 2 is the equation of motion. Then we get to a step 3, which we need to find the natural frequencies. So the natural frequencies, so finding the natural frequencies We need to solve for determinant of matrix K minus M omega square equal to 0. Remember, the damping has nothing to do with the natural frequency, similar to 1 degree of freedom. In 1 degree of freedom, no matter you have damping or you don't, your omega n is always K over M. Although you have, later you find that you have omega d, which here is the same, but we'll just focus on finding omega n. So we'll solve that one, and the result would be omega equal to K over M and omega equal to 3K over M. So as a convention, the smallest one, we sort them from small to large, and we call them the low frequency and the higher frequency. If you have more, similar manner. So omega 1 and omega 2. Step number 4, and again, I skip the algebra because it's easy. You just substitute them, you will get this result. So step number 4, we need to find the modal matrix. The modal matrix, we need to have the mode shapes. So we need to solve the K minus M omega squared x1, x2 equal to 0. Right? The same matrix that we had, this time x1, x2. So from here we can find, let me move that guy there. The ratio of x1, x2 when my omega is equal to omega 1, which it gives me 1, x2, x1 divided by x2, when omega is equal to omega 2 gives me minus 1. Later, please go home and check my calculation, make sure that I didn't do any mistake, and these numbers are correct. All right. So trusting my calculations, I can form my modal matrix because I know my mode 1 is 1 and 1, and my mode 2 is 1 and minus 1. Okay. So this was the convention and a way to show them. Again, you don't have to show it like that, but this is what most of textbook they use to show them. They call them mode 1 and mode 2. And by the way, there is no difference, like if you have a minus 1, if you put the minus up there or down there, it doesn't matter. Right? Remember the way that we decide to do this x1 over x2, we set one of them to 1 and we find the other one. So it doesn't matter which one you set to 1. They don't have to be, one of them doesn't have to be 1, as we discussed before. So your modal matrix is, which we showed it by U, is a matrix which each column is one of these mode shapes, is 1, 1, 1, minus 1. All right, so that's our modal matrix. And that's a key things in any system that let us to decouple the system. So also we discussed last day that each of these are the eigenvectors. And each of these numbers are the eigenvalues. As we discussed, we said this is a physical system. We didn't know that they are going to turn out to be eigenvalues and eigenvectors. We just solved them. But we said if you show these equations to a mathematician without telling them that this is a stiffness matrix, this is a mass matrix, you just tell them that we have these two matrices and we use this equation, the determinant of K minus M omega squared equal to 0. And also we solved this equation and we found, we did all these things. They say, well, that's the definition of eigenvalues and eigenvectors. Okay, so step number 5 is we need to decouple everything. So I have a mass matrix, my decoupled mass matrix. One thing that you need to remember, our mass matrix is already decoupled, but still it has to go through the new equations, all right? So it doesn't matter if it is already decoupled. MD is UTMU. Because remember, we are transforming everything to a new system. Right. Let's say converting let's say decouple, I want to say decoupling. So UTMU, you have your U matrix, you have your M matrix. It gives you, I did the calculation before to save some time, it gives you that. You repeat the same things for A. K will give you 2K, 0, 0, and 6K. And damping will give you 2C1, 0, 0, 2C1 plus 4C2. Please again, go home and check my calculation, make sure that I didn't miss anything and the numbers are correct. So this is MD. KD, remember we use the same formula, U transpose K, original KU. And CD the same, UT transpose CU. Okay, so now good news. The matrices, they are all diagonal. Diagonal, diagonal, and diagonal. Right? And why it is good? Because when we write the equations, they are independent. So step number 6. The principal coordinates. Remember we said if we use this transformation, x equal to uv, vector x and u, our new coordinates. Mathematicians, they call them principal coordinates because they are in direction of eigenvectors. For us, they are just some coordinates that doesn't have any physical meaning, right? This is important to know. Let me write it down and I'll explain it. So if I write down my equation, they will be MD y double dot 1, y double dot 2, CD y dot 1, y dot 2, and KD y1, y2 equal to 0. So from here, obviously, when you do the multiplication with matrices, you will get two independent equations, right? So you will get one equations for the first one, 2m y double dot 1 plus 2c1 y double dot 1 plus 2k y1 equal to 0 and 2m y double dot 2 C1 plus 4C2 y double dot 2 plus 6K y2 equal to 0. So imagine we have the numbers and the values for each of them. Now for each of them, I know the mass, the damping, and the stiffness. I can do all the calculations that we learned before. And if, for example, this question gives me the initial conditions or other things, I can find y1t. And from this one, I can find y2t. I have y1, I have y2. I need to convert them back. Step 7, convert back actual coordinates. Which simply what we need to do is our actual coordinate x1t and x2t. Again, the U matrix multiplied by y1t and y2t. So if you notice, I use the word actual coordinates. Remember, x1 and x2, they have physical meanings. They are coordinates that in the schematic, again, I want your attention for a second, right? In our original schematic that we have, x1 and x2, they have meaning. We can see them, we can measure them. But remember, y1 and y2, they don't have any physical meanings. They are just principal coordinates. They help us to solve the equations, but we need to convert them back. So this one, they're all math and no physical meaning. All right, so that's the case with damping. Now you can see the previous example and this one, if you have n degree of freedom system, it has damping, it has, let's say, external forces, no problem. We convert them to 1 degree of freedom system and we spend almost half of the semester on 1 degree of freedom system. We know how to deal with them. Right? So that's the, almost we are done with what we need to do with n degree of freedom system. Okay, now I'm going to stop here to see if you have any question. Any part is not clear. Okay, silence is a good thing. So, but here is the deal. We are not always that lucky. Sorry, Terry. Oh, you are right. Sorry for the rush. I'll give you a moment to finish writing. So just as a quick check while are writing. So what's your feeling so far? Hopefully you don't feel overwhelmed by all the new materials. If you just feel that you understand the steps and the logic, that's okay. Then all you need to do is just a practice, solving one example. And that should be enough. Again, we emphasize a lot. We use the 2 degree of freedom system, although the title of the topic, the lecture, the chapter is n degree of freedom system. Main reason is because working with 2 ID matrices is easier. Right? But the same thing will be used for any degree of freedom system. Of course, in your exam, I'm not going to ask you more than 3 degree of freedom system. That would be cool, right? You will find all these eigenvalues and solve equations. We'll use computers like the project that you need to solve into the 7 degree of freedom system, but the same exact steps. But let's deal with crisis about damping. And damping considered to be the sort of the nasty part when we do vibration analysis. And the reason is dampings or damping matrix may not always turn to diagonal. Like here is an example that we solved it before, except without damping. If I write the equations and find the damping matrix, it will be C1 plus C2 minus C2. I leave it to you to later draw the free body diagrams and see if you can find the same damping matrix. But it's obvious that's my damping matrix. And I have some values which I put them there, and C1 plus C2 gives me that C2, and this one is C2. So that's my damping matrix. So before we had our stiffness and we found the U. Was previous example. Yes, it was. Let me move back to make sure. It was example, this one, 21. Okay. So we don't have to write the equations before. 21. We found the U matrix, which U was 6, 6, 6, 7, minus 1, 1, and 1. So before we tried it with MD, with the mass matrix and with the stiffness, no problem. But let's try it with CD. CD is U transpose CU. The result will be minus 1, 13, minus 1, 13, 1, 56, 2.7. And please again, check my calculations, make sure it is correct. However, the point is, the matrix is not diagonal. So this is what we will say. We say our original damping matrix, the damping matrix not diagonal. No, that's not sure if this is correct. You're not able to diagonal anything. So what should we do? Well, this is where we have to rely on numerical solution. There is no analytical solution. Nobody can really solve if your matrix is not diagonal. So that's why numerical solution. Why emphasize? Go to your tutorial 7 and the next example that I will solve, Jacob will show you how you can use MATLAB or Python to deal with when your matrix is not diagonal. Okay, so he's going to go through a step by step, but it's not part of something that you will be asked in the exam. Okay? You need it for your project. Your project is an actual car system, and the matrix is not going to be diagonal. So you need that tutorial 7, please, either today or if you are on Monday, go to that session. Okay, it will show you how you can solve for that one. But I will come back to this idea. And one thing you may ask, how do we know if a matrix is, if we can diagonal a damping matrix or not? So of course, one way is to check it. Check to see if C E is diagonal. Because when you did all the hard work and you found your modal matrix, all it takes, you try it for the CD and see if it turns out to be diagonal. The second approach, there is a condition C must satisfy a certain condition. And that condition is matrix C must be proportional to your matrix K and your matrix M. But this is too much. I don't want you to study this topic. This is more in grad school. We'll go through that one. But in a very simple word, as a quick check, whenever your damping matrix can be written as coefficients of your mass and your stiffness matrix, we'll see mathematically the CD will be diagonal. And there is a terminology people use, if you just want to write it down, just to know. It is called proportional damping. Like by chance, it happened that you deal with a system that your damping is proportional. It means that it is proportional to K and M, which rarely it happens. That's why nobody so much cares. Sometimes we are lucky, the matrix will be diagonal, sometimes not. That's why the numerical solution is our friend. Okay, so section 5.7 is just a computer solution. I just wanted to show you how easily you can use computer to find the eigenvalues and eigenvector. I'm sure you're all master in using MATLAB or Python, and you need it for your course final project and also for the experiment. So simply you need to, from MATLAB, you need to calculate the eigenvalues and eigenvectors of K and M. Just 2 lines gives you the eigenvalues and eigenvectors. Something that you need to be careful, MATLAB does not sort them for you. You need to sort them. Remember, from the smallest to largest. If you just use them from U1, U2, you're going to mess up with the everything, and you will see your matrices will not be decoupled. That's all. Now what I want to do, I want to solve one example, example 22, one complete example. So you will see all these steps together. Okay, I want your attention for the next 15 minutes here. And at the end, we will see what it is. The damping here is not diagonal, which hopefully in the afternoon you will go to the tutorial and see how you can solve it in MATLAB. So I have this 3 degree of freedom system with all these numbers. And by the way, there is a typo here. Please correct it. And this is radian per second. Omega is radian per second. That was just a typo. So step number 1, draw the free body diagrams. That should be easy for all of you. So I have this big mass, then I have these 2 masses. So I might have moved one of them more than the other, doesn't matter. And remember, when we show something like by x3, it means that already we agreed that there is a constraint here. Because we intuitively get a feeling that this 2m is more like a beam or like a bar, and it's going to tilt. But when the question tells us that there is only x3, it means already it is inside the rail and it can only move ups and down without tilting. Example 23 is an example where this 2m can also tilt. All right? That's next things to be worried. And the same with m. With two other masses. Just for simplicity, we show them like that, but we assume that they are inside the rail and they can only move ups and down without moving to the left or right. So like before, you disturb them, right? And remember, you have also an external force and you have damping. So the most complete case for an n degree, which is a 3DOF here, 3 degree of freedom system. So quickly, let's draw the reactions here. So I'm going to end up with two forces there, two forces over here, their reactions, two forces there, and their reactions. So we shouldn't forget that we have also an external force that goes there, F sine omega t. So I have here kx3, cx dot 3, right? And for this one, I have x1 minus x3, x dot 1 minus x dot 3, and this guy over here is going to be k x2 minus x3 and c x dot 2 minus x dot 3. Okay. All right, so and that's the damping. So remember, you need to make an assumption. Like here, for example, I assume that x1 is bigger than x3. That's why my forces are all tension. And here I assume that x2 is bigger than x3. This is an assumption just to draw the free body diagrams. You can assume the opposite, but you have to be careful about the direction of these forces. So we have the free body diagrams. We know what to do with each of them. That's the Newton law. Sum of the forces is equal to ma. And I leave it to you to, oh, okay, you are still writing, I guess. Sometimes I guess my speed of writing maybe is faster than you. So. All right, so we have the free body diagrams. You know what to do with them. Sum of the forces is equal to ma. That page is for you. And we will get to step 3. So we have our matrices. Right? Our matrices now are 3 by 3. And if we check, we realize that the mass matrix is diagonal. And it seems they are in order and correct. So that's a quick check. Always in your exam, I suggest do that check because it gives you a hint if you made a mistake somewhere. So the damping, right? Each element on diagonal should be the sum of the damping, which you can check. And off diagonal, they must be with minus sign, right? Let's check one of them, for example, to make sure. This has to be the damping between 1 and 3, right? It's in a matrix, it is 1 and 3. So let's check between 1 and 3, what do we have? Between 1 and 3, between these two variables, between these two masses, I have damping C. What about between 2 and 1? 2 and 1, I don't have anything connecting them, right? So that's why you will see in my matrix, 2 and 1, I don't have anything. So a quick way to check is, you know, this is your first row, second row, third row, first column, second column, and third column. So each matrix, each element, you can quickly check which one is which. And if you don't want to do that, that's okay, if you are sure that your equation is correct. So the stiffness matrix, again, is not diagonal. You can check the parameters. And also we have excitations. Or external force. This force, they don't have to be harmonic, they can be anything. Because later when we use computer to solve them, you saw in previous chapter, we don't care if this force is harmonic or not. So remember, we don't have anything for the second mass and third mass. All right, and this is what we have. Let's go back and double check. There is nothing external on the second one and on the third one. The only things that we have is for the first one, right? And that guy here. So which means everything is checked and correct. But still, I encourage you to do all the math and make sure my calculation here are correct. So we have the matrices. Now the next step, you know what to do. You've solved the equations, but you don't need to do it because it's 3 by 3 is too much. We just use computers and we can find the omega n1, omega n2, and omega n3. Just remember, more than 2 degrees, you use MATLAB because there is no point writing the equations. And we have all the value for M and C and K, and I put the code on Canvas so you can check it. The next step, your eigenvectors, which gives you the U matrix. So I had a 0 over there. So if you got a 0, do not freak out. Sometimes it happens. Remember the meaning of the modal matrix? The modal matrix was if my system vibrates with natural frequency of omega n2, which is 10 hertz, then the first mass, the second mass, they are going to move in opposite direction. The third mass is not going to move at all. So that's the meaning. Maybe next lecture, I will show the simulation of that thing so you will see that one. So, and after that, you know what to do. You have your modal matrix, right? You have your modal matrix. MD, which is UT and U, CD, which is UT and U, and K diagonal is UT and YN. No, sorry, it has to be C and K. I hope I didn't make the mistake before. No, correct. All right. Sorry, just was a quick check. All right, so we have the modal matrix. We can diagonal our matrices. So just one thing to remember when you use MATLAB, please check that one. You will see that your mass matrix is equal to I matrix. Okay. So only in MATLAB. In MATLAB, always MD is equal to I matrix. Like here in this example, it will be 1, 1, 1, and then the rest 0. The reason is that MATLAB divide everything, so you get like divide everything by mass matrix, so you get like an I matrix for M. That's the way MATLAB does it. So you ended up with several equations, which in this case, there are 3 equations. You have your initial conditions. So here is our new equations, and they are all in principal coordinates. In principal coordinates. All right. So what happened? We have a 3 degree of freedom system. We derive the equations. We use MATLAB to find the modal matrix. That modal matrix did the magic for us, and we coupled these equations. I showed you in the lecture before that you can also use the modal matrix to transfer your initial condition. Remember, now we have to move everything to the principal coordinates. Principal coordinates, the one that they are in direction of the eigenvectors, right? Which we just use math, and the rest is easy. So we have 3 equations with their initial condition. You learn before how to solve them. However, you don't have to solve them by hand. You just use MATLAB and ODE, which again was something that we discussed before in previous chapter. So as I wrote here, you use MATLAB ODE 45. Please check previous chapter if you missed that section, which we had an equation, and I showed you how to use ODE 45. And you're done after that with just putting everything together. Okay, so your final result, your actual result is like this one. Since MATLAB will do all of this for you, it is important to, with a 2 degree of freedom, my previous example, do it one time manually by hand and try to understand everything. That's something important. I encourage you to do that. Otherwise, you will get the correct answer with MATLAB, but you have no sense what's really happening. All right. So, and here is what you have to do. Take a look at this one. It's exactly similar to the previous one, but only we have one damping here. If you write the equations, you will see, and you follow all those steps, you will see your damping is not diagonal. So you cannot diagonalize it following that U matrix. So that nasty matrix that I told you. And this is your TA is going to show you today afternoon how to solve this one in MATLAB, right? Which is going to be numerical solution. He will teach you and all the logic behind it. Again, this is not required for your exam, but it is required for your project. So that's why I said this is essential. Attend today or Monday session if you are in Monday to learn how to solve this one. Thank you very much for listening. And one last thing, I will, this weekend, if I get some time, I will put the solution for example 23, 24, and 25 on Canvas with the notes, right? I'll put the solution for them. Before checking my solution, please try to solve them and then check with my solution. Thank you very much. All right, thanks. You too, bye.
About the material like for the string, like is it any string that can change the
Because it's not heavy, yes, any string can hold it.
carbon string?
Carbon string, that's good. Like the floss also, teeth floss, you can buy from. No, the floss is well. But yes, any right. Dental floss. Go with that one. All right, so let's me stop that one. Can we go outside to make sure that the next teacher